Welcome back. We are going to now look at a new concept that is related to arguments as well. So we have looked at validity, we have looked at natural deduction rules, the truth table. Now we want to look at the concept of satisfiability. So the generic interpretation of satisfying in English means to, if you are going to satisfy the requirements, right? You need to meet at bare minimum the minimum requirements that are being required, so as to say. So satisfaction in this case, we're going to define it in the following manner. So we're going to define it as the possibility to find an interpretation. Then when later on, when you look in the next chapters, a model, an interpretation or a model that makes the formula true. So as long as you can find a model or an interpretation that can make it true, then we say it is satisfiable. Right. So a direct translation of what they're trying to say is that you are looking for a path that will make it happen. As long as you have a path that will make it happen, then you can say it is satisfiable. Right? It does not care how you do it. If you go wrong 999 times, as long as there's that one path that it is possible for it to be done, then you can say it is satisfiable. So a statement or an argument can be not valid but still satisfiable. Right? How do we look, or how do we see satisfiability from a truth table? Right. So if we have a truth table, and I will show here validity and satisfiability, right? If we have a truth table, as long as sorry, that's it. As long as there exists a true valuation as a conclusion. Right. Then we say it is satisfiable as long as there exists a true valuation as a conclusion. Right. Another way to discuss it, we can say all arguments that are not contradictions. Arguments that are not contradictions. Okay. So what is a contradiction? You know what a contradiction is, something that will always be false. As long as there is at least one true, right? If there is at least one true conclusion, then we can say it is satisfiable. There is a means that you can get to a conclusion. So far we've seen the premise, we've got the conclusion, we've got validity, and we've got satisfiability. Right. So what is the difference between the two in terms of operations? So we have true, true, false. We need another row here, false. Then also you need true, false, true, false. So validity, we say it's valid, not valid, valid, valid. Satisfiability checks, and we can say this is satisfiable, satisfiable. As long as there exists one true statement, we say it is satisfiable. Right. So one true conclusion, we say it is satisfiable. Right. So that is our simple definition of satisfiability. Now, satisfiability is much more achievable than validity in our day-to-day world, right? I'm going to touch on that topic when we look at chapter 2, when we start looking at models, why satisfiability is much more important, is a very important concept under logic, right? Now, why are we looking at satisfiability? Right. There's a concept called the Horn formula algorithm, right? So the Horn formula algorithm, what does it do? It checks whether or not a formula is satisfiable. So now there's two ways we can check satisfiability, using a truth table or using the Horn formula algorithm. Right now, in the event that you are given a formula that has got a lot of inputs, it might take longer to do the truth table than it will take you to do the Horn formula algorithm. Right. But in the exam, they'll definitely ask the Horn formula algorithm, and you have to know what the Horn formula algorithm is and be able to do it. So a Horn formula is a formula phi of propositional logic if it can be generated as an instance of H being the Horn formula in this grammar. So P, right? What is P? P is a propositional statement, right? And then A, right, will consist of propositional statements and the conjunction of propositional statements, right? Then C, this represents a clause, right? A statement written in the form of A implies P is it's a clause, right? Then we've got the Horn formula, which is a clause or a conjunction of a clause and other Horn formulas, right? So don't take much to heart about the notation that is used here. It's just definition for the sake of informal definition. That's how it's defined. Right. So the algorithm or the Horn formula algorithm, right, will work in the following manner. Right. It is going to maintain a list of all occurrences of P of propositional statements in a formula, and it will do the following. Right. So your formula, you're given a formula, it can be, all formulas rather, can be written in the format of conjunction of clauses. Right. So you've got P implies Q, you've got Q implies S. Right. All formulas can be written as a conjunction of clauses or in the Horn or as a Horn formula. Right. Any statement can be given as a Horn formula. Right. So maybe before we move to that, I can share with you the concept that you have to look at. We've got conjunction normal form, we've got disjunction normal form. So this concept we looked at when we're in 2661. If not, under additional videos, you'll see a few videos that you can also watch for conjunction normal form and disjunction normal form, right? But the short pointers are that you can have statements like A implying B. These are equivalent to not A or B, right? Then you can also have, so if you have got, this means that all the clauses that we have are disjunctions, more or less, right? So you can have any statement that is now written in conjunction normal form, right? So we've got all the statement written in conjunction normal form where we've got conjunction of different disjunctions in there, right? So if you have a conjunction, for a conjunction to be true, all the given clauses have to be true. All the clauses in the conjunction have to be true. If this is false, then the whole statement becomes false. Right. So that is the power of a conjunction. Right. So now we want to use that to our advantage. say we are then given a statement that is in one formula. So it will be a conjunction of clauses. So we want a scenario where each and every clause is proven to be, or the formula as a whole, if it is satisfiable, then it should not lead to a contradiction. Right. And how do we do it? So it says mark T if it occurs on the list, right? And I want us to do this with an example so that, we can catch it quicker. Right. So let's look at an example over here, right? And then we want to have this one over here. Okay. So it says mark T if it occurs on the list, right? If you have a formula that have got a tautology or something, a T, right? Mark it. So we're gonna mark it blue. So we'll say mark T blue, right? If there is a conjunction of P1, P2, and P what, implying P prime of phi such that Pj for j is equals to 1 to ki are marked. So if all of these are marked, then mark P prime. So T is marked on this one. Everything on the left is marked, then mark everything on the right. That is the short English form of it. If everything on the left of the implication is marked blue, then mark what's on the right blue. Right. So why are we marking T? T is guaranteed to be true. If this is true, then this has to be true, right? Then you can also now, the next step we've marked T, we now need to mark S, right? Based on number 2. Then otherwise, if there's no conjunct, then go to step 3. If this is marked, then print out the one formula as unsatisfiable if a contradiction is marked, and stop, otherwise go to 4. Right. So if there is a conjunct such that all P Pi, all the P's on the left hand side are marked, mark P as well and go to number 2. So you need to repeat this. Now S is marked, we need to mark every other occurrence of S. Right? So we've got S is marked, S is marked. Cool. Then now we check again, S is marked, okay, cool. So Q, we're not going to mark Q here. So S is marked. Then we've got S over here. We are marking Q now, and then we mark all the other occurrences of Q. Right. Then in this case, R is not marked, P is not marked, right? So now what you can see is that everything is marked, and we cannot repeat step number 2, right? If contradiction is marked, is contradiction marked? No, it's not marked. Then print out the one formula is unsatisfiable and stop. Otherwise, go to step 4. So we're not going to do this step because this is not marked. Print out the one formula is satisfiable. So we can say one formula is satisfiable. One formula is satisfiable. And then you stop. So I'm gonna repeat the rules in a much more better English than the one that is given there. So mark all the occurrences of T blue. So this is straightforward. Everywhere there's a tautology or is given a tautology, mark it blue. Then if there exists a clause where everything on the left is marked, then mark the atomic statement on the right blue or whatever color, right? And then mark all its other occurrences, right? Mark all its other occurrences. Then if you are done, repeat again step 2. If everything on the left is marked blue, then mark what's on the right blue and mark all its occurrences blue, right? If you repeat again number 2 and then you find that there's not much more to mark, then what do? You check at the end of this, is the contradiction marked? If it is marked, then we say it's unsatisfiable. If it is not marked, then we say it is satisfiable. Right. So the one formula is in fact finding whether or not a given formula is satisfiable by checking whether the statement of the formula is a contradiction. If you have got true implies false, then the resolution is false. And then if one of them is false, then all of them, the whole statement becomes false by default. So that is what the one formula is supposed to do. And once we use it, we can determine satisfiability. And for a question that comes with 6-7 marks in the exam, it can be an easy 6-7 marks from us. Right, cool. This brings us to the end of chapter 1. Let's meet again when we start with chapter 2.